Hi, I'm a mathematician, not an epidemiologist. But I like to think about how mathematics is used to describe all sorts of things. So in this video, what I'm going to do is I'm going to describe how you can use mathematics to build a very simple model of disease transmission, why it does not work to model COVID-19, and how you can change it to do better. So welcome to How to Model COVID-19, Fail, and Learn Something. To begin with, we're not going to talk about disease transmission at all. Instead, we're going to think about a rumor traveling through a school.
Here's a school. It has a bunch of students in blue who don't know a rumor, and there's one student in red who does know the rumor. We want to study how the rumor spreads. We could just go with the person who knows the rumor tells two people, and they tell two people, and they tell two people, and so on, and so on, and so on. But that's actually not a good technique when we have a limited population, because you run out of people. Instead, let's focus our school down to just a couple of individuals, 2 people in red who know the rumor, and 3 people in blue who don't know the rumor. Let's think about how the rumor can spread. The top person in red can have 3 possible interactions with people who don't know the rumor. Same thing with the bottom person in red. That is 6 possible interactions between people who know the rumor and people who don't know the rumor. But not all of those interactions are going to result in the rumor being spread. I mean, sure, there could be a megaphone, "Hey, listen to this rumor." But not all of those interactions might happen. And even if they do happen, not every single interaction will result in the rumor being spread. For example, we might assume that about 17%, or 1 out of 6 interactions, will result in the rumor being spread. In that case, we'll just have 1 new rumor knower. This is the basis of what's called the Logistic Model. The number of new people who know the rumor is a fixed fraction or percentage of the number of possible interactions between people who know the rumor and people who don't. That's the logistic model. And you can solve the logistic model. Here we go. I'm going to trigger some Calculus 2 students as they remember the method of partial fractions to get a solution. You don't need to know this, but let's look at what the solutions tell us about how the rumor spread. This is a solution to the logistic model. Just to orient yourself a little bit, we're going to assume that we're starting with one case. That's where the red curve starts. And then we've got a school that has 100 people in it. Right now, I'm assuming that that fixed percentage is 3%. So you can see when 3% of the interactions between those who know the rumor and those who don't result in the rumor spreading, after about 4 days, everybody knows the rumor. The rumor spreads. If we go crazy megaphone mode, whoa, boom, almost immediately, everybody knows the rumor. It's just so obvious. If we take that percentage down to 0%, then that means the person who knows the rumor never spreads it. So the number of rumors stays at 1. But if we raise that just a little bit, so at 1%, you can see that even with only a very small fraction of interactions resulting in the rumor being spread, after about 9 days, almost everybody knows the rumor. Here's one more feature of the logistic graph. And to show it, I'm going to set our fixed percentage at 4%. What I want to do is flip this switch to turn on new cases. So I'm showing the number of new cases per day in green. And what you can see is that we start off with a low number of new cases per day. And then we have a large number of cases per day. We've got a peak. And then the number of new cases falls until it's very, very small because almost all the students have heard the rumor. That peak happens about the time that the number of people in the school who know the rumor is half, 50 out of 100. And that's true of the logistic model. What happens when we change that 1% to 4%? The graph in red still shows everybody getting the rumor,
knowing the rumor. It starts off slow growth, then speeds up till we reach about the halfway point. And then we've got more growth, but that growth slows down as we reach the max of 100. The highest amount of growth per day is shown in green is when we hit half the school. And the green graph shows the number of new cases. You can see it's not as high and it's much more spread out. Here's that 4% curve again. You notice that we've got a very high peak. A lot of people are spreading the rumor. The rumor ICU is full. There's lots and lots of drama as lots of people know the rumor. But when we move back to 1%, there's not a lot of drama. The peak is not that high. The drama is spread out over many days. You've probably seen this before. This is the type of curve people have talked about when they've talked about flattening the curve, reducing the number of new cases per day so that we don't overwhelm a healthcare system. Did we do it? Do we have a good model? Does it model what we see in the real world? Sadly, no, it doesn't. Here's the data from Louisiana for the first couple of weeks of the COVID-19 pandemic. And on the left, you see new cases. That looks like the graphs we saw when we turned on the switch. And on the right, you see something that looks similar to a rumor traveling through a school. Here's the new case graph, not just for the beginning of the COVID-19 pandemic in Louisiana, but up until about the end of June. And you can see it does not look like our model. Instead of the new cases going down to 0, we've got a resurgence of new cases. Moreover, that peak in new cases is supposed to happen when half the state of Louisiana has been infected by COVID-19, at least according to the Logistic Model. And that peak occurred when nowhere near half the population of Louisiana had COVID-19. So how can we change the model? What do we need to do a better job of modeling how this virus travels through a population? Well, to start with, we can think about what we're saying about people in our model. A student in the school starts out susceptible. They don't know the rumor. And then they hear it and they become infected. And once they're infected with the rumor, they know the rumor and can spread the rumor for the rest of their lives. And that's not really how infections work. Mind you, that's how some fictional infections work. Once you're a zombie, you're always a zombie. Once you're a vampire, you're always a vampire. And there are some actual diseases that spread where once you have it, you can spread it for the rest of your life. But for a lot of infectious diseases, that is hopefully not the case. What we need instead is a new category of person. You start off susceptible, you become infected, you know the rumor, and then you move into the recovered category. And by the recovered category with rumors, we mean you're rumor agnostic. You don't care about the rumor, and you're not going to spread it to anybody else. This is what's missing in our logistic model, the idea that you move from susceptible to infected to recovered. Now, epidemiologists don't work with stick figures. Instead, what they work with are what are called compartments, boxes. One box for the susceptible population, one box for the infected population, and one box for the recovered population. And what epidemiologists do is try and figure out how you move from one compartment to the next compartment to the next compartment. If you're interested, this is what's called the SIR Compartment Model. You can Google this and find a lot more information about a model that's still probably a little bit too simplistic for COVID-19, but gets closer to how some people model. One of the reasons that peak occurs in new cases when half the state of Louisiana has not been infected might be because a lot of people recover and therefore stop spreading the disease. But there's another issue. Back when we started, the logistic model used a fixed percentage. So there was always a fixed percentage of interactions that would result in the virus being spread. But that's not true in the real world. When the pandemic started, we didn't know about it, and so there was probably a good chance of virus spread. We had a high percentage. Then the state of Louisiana shut down, and we probably had a very low percentage. And then as the state reopens, we've had differing percentages throughout the state as more and more contact has been allowed.
our model assumed a fixed percentage, when maybe what it should have been doing is thinking about how that percentage could change given different circumstances. This model up by Johns Hopkins University shows that type of thinking. The effectiveness of social distancing decreases by 25% depending on the type of orders used. This is what happens in mathematical modeling. You try to model something, you don't capture everything you want to capture, so you make adaptations, you make changes to produce better and better models. And I'm pretty sure this is what's happening time and time again with the people trying to model COVID-19. So if the models change, don't be surprised. Thank epidemiologists for working so hard to make the models better and better. If you want to use the Desmos calculator that I used in this video, there's a link in the description. If you're interested in COVID-19 models, I strongly recommend this site at 538.com, where they look at a variety of different models, the assumptions, and even how they break down state by state. Thanks for watching, and stay safe.